Hi everyone, welcome back to Chemical Engineering Statistics. So in the previous section, we already discussed about statistical inference for two independent samples. Now we will discuss the statistical inference for two paired samples. So what is paired samples? So paired sample means that the observations for the paired sample are taken under homogeneous conditions. However, the conditions may change from one pair to another. So for the example here, we can see that we have a problem or we have a data of weight measurement of students in their freshman year. So these students are weighed in April and in September. The weight of all students are measured. So let's say we have student A, student B, student C, D, and E. The weight of student A in April is 66. The weight of student B in April is 52. The weight of student C in April is 68, and so on. On September, that 5 students are weighted as well. So the weight of student A in September is 67. The weight of student B in September is 53, and so on. So this is the case of pair sample. We measure the weight of the same students but at different conditions. Another example, if we have 3 subjects. So these 3 subjects change their lifestyle, and then we measure the weight, the fat composition, and so on from this subject before they change their lifestyle and after they change their lifestyle. So the subject is similar, subject A, B, C, but we measure the parameters on different conditions before they change their lifestyle and after they change their lifestyle. So here we can see that sample A and sample B, or maybe we can say sample A is before treatment and sample B is after treatment, are related. Yeah, we have sample X1A, which is related to sample X1B, sample X2A, which is related to sample X2B, sample X3A, which is related to sample X3B, sample X4A, which is related to sample X4B. So these two sets of samples are given two different treatments. So the resulting samples can be categorized as paired samples. The hypothesis test for paired sample is done based on the average treatment level differences. So the null hypothesis for the paired t-test for the paired samples can be written as H null is the mu d equal to delta 0. Okay, delta 0 is often assumed as 0. Okay, so mu d equal to 0 means there are no difference between the samples before treatment and the samples after treatment. The test statistics for the pair t-test is shown in equation 516. So this equation can be obtained from the Montgomery book, our textbook. So T0 equal to d bar minus sigma 0 divided by St divided by square root of n. The D bar is the sample average of the n differences D1, D2 until Dn. So, how to calculate D bar? To calculate D bar, first we need to measure what is the difference between x1b minus x1a, and then what is the difference between x2b minus x2a, and so on. The differences is summed up and then divided by 4. So that's the D bar. That's the sample average of the n differences D1, D2 until Dn. SD. SD is the standard error of these differences. The alternative hypothesis, the p-value, and the rejection region for the fixed level test can be obtained on this slide as well. So another example is the drinking water problem. So in this case, we measure the zinc concentration in the bottom water and in the surface water. The bottom water and the surface water is the water obtained from the same region but at different position, whether it's in the surface or in the bottom. So here we have 10 different regions. At each region, we took sample of the bottom water and the surface water. We measure the zinc concentration, and this is our data. To determine whether there is any differences between the zinc concentration on the surface water and the bottom water, we conduct the pair t-test. So first we set up the null hypothesis, which is mu d equal to 0, and the alternative hypothesis, which is the mu d more than 0. Then we define our significance level, alpha equal to 0.05. Based on that data, we can calculate or we can determine our critical T. We determine the critical T using the T table by using alpha 0.05 and degree of freedom 9. Because we have 10 regions, so our degree of freedom is 10 minus 1. It's 9. The critical T is 1.833. Then we calculate the T statistical test. Here it is denoted as T with a star. So our calculated T is 4.86. This means that the test statistics falls in the rejection region, and then we have enough evidence to reject the null hypothesis. Then for the conclusion, we can say that on the average, the bottom zinc concentration is higher than the surface zinc concentration. We can get these conclusions because in step 1, we define that D is the difference at the bottom and the surface. So that's the zinc concentration on the bottom minus the zinc concentration at the surface. Okay, when we reject the null hypothesis, means that there are a higher zinc concentration at the bottom water than on the surface water. That will give us mu d more than 0. So that's all for now. See you on the next video.